In this video, we're going to focus in on giving an answer to a question that we've been asking for a while, which is, when are two f bracket x modules isomorphic? And the setup here, this is theorem 15 in section 12.2, is that we'll have the same n-dimensional vector space V over a field F and two different linear transformations, S and T. So they're linear transformations. They may be different. They may be the same. And we're going to prove that three things are equivalent. One, S and T are similar linear transformations. Two, the f bracket x modules obtained from V via S and T, that is, how do you turn V into an f bracket x module? You need a linear transformation. So S turns V into an f bracket x module one way. T turns V into an f bracket x module another way. Same vector space, maybe different linear transformations. The second claim is that the f bracket x modules obtained from V via S and T are isomorphic f bracket x modules. And the third one is that S and T have the same rational canonical form. So if you have one vector space V and two different linear transformations on that vector space, how do you check whether or not those linear transformations define isomorphic f bracket x module structures on that V? One way to do it is to compute the rational canonical form for S and for T and see whether they're the same. So we'll prove this by proving 1 implies 2, 2 implies 3, 3 implies 1. Let's do 1 implies 2 first. So let's assume that S and T are similar linear transformations. What does that mean? Well, that means that there's a non-singular linear transformation U from V to itself such that S equals U, T, U inverse. So the way that we're actually going to use this is by saying, OK, if we now apply U on the right to both of these, that means that S following U is U following T. So U is a non-singular linear transformation from V to itself. That's a vector space isomorphism. So that's one of the equivalent things that we proved talking about linear transformations. And what we're going to show is that it's also an f bracket x module homomorphism. Well, we have to say what that means. So we need to know, how does x act on each of these V's, the first one and the second one? And usually, when we talk about a linear transformation, turning V into an f bracket x module, x acts the same way on both of these copies of V. But here we're going to have x act as T on the first V and x acting as S on the second V. So for concreteness, like, what does that mean? We need it to be that we apply this linear transformation to some polynomial acting on a vector V, and that's the same thing as if we first apply the linear transformation and then act by the polynomial. So like, what happens if you pick the particular polynomial x? We apply to U to x acting on this vector V. That's U of T of V, because x acts as T on the first copy of the vector space. So what is that? Just moving parentheses. That is U of UT of V. And now UT is equal to SU. That comes out of S equals UTU inverse, S and T being similar. So that is SU of V, which is S of U of V. U of V is in the second V over here. So how does X act on something in the second V? X acts as S on this second V. So S of U of V is X acting on U of V. So this is the kind of thing that we need to check. But we don't just need to check it for x to the first power. We need to check it for any polynomial P of x. So, OK, how do you go from the first power to a higher power? I'm not going to do all the details here, but I'm going to put in more than are in dominant foot. Well, U of x to the k acting on V has to be the same as x to the k acting on U of V. So what is x to the k acting on V? Well, x to the k is, x acts as T on the first V. This x to the k is going to act as t to the k on the first v. So what do we know about t to the k? S to the k is ut u inverse to the k. And this is just like something that we saw in the last lecture when we were talking about how similar matrices satisfy the same minimal polynomial. This is u t to the k u inverse. So now this is u t to the k acting on v, and u t to the k is s to the k u. So you can use this now and see that, in fact, this is going to be x to the k acting on u of v. And now you can extend by linearity and see that this really is an f bracket x module homomorphism. So what do we need? We actually want this to be an f bracket x module isomorphism. But it's certainly injective and surjective because u gives an isomorphism of vector spaces. So this map from v to v is injective and surjective. So we have an f bracket x module homomorphism that's injective and surjective. So it's an f bracket x module isomorphism. All right. So I'll pause and erase, and we'll prove 2 implies 3 and 3 implies 1. Now let's suppose that the f bracket x module is obtained from v via s, and the one obtained from v by t are isomorphic f bracket x modules. So let's call the first one v1 and the second one v2. Since v1 is isomorphic to v2, well, what are these? These are finitely generated f bracket x modules, in fact, torsion ones. Then the classification for modules over a PID, and in particular, the uniqueness part for the invariant factor form, says that they have to have the same list of invariant factors, that the invariant factors are classifying these modules up to isomorphism. And now, okay, if they have the same invariant factors, they have the same rational canonical form, because the rational canonical form is determined by the invariant factors. If I tell you the invariant factors, then you know the rational canonical form. So they must have the same rational canonical form. All right. Let's do the last piece, 3 implies 1. Let's suppose that S and T have the same rational canonical form. So what does that mean? There are two bases, B and E of V, such that you take the matrix of S with respect to B. What is it? It's the rational canonical form of S. And you take the matrix of T with respect to E. What is that? The rational canonical form of T. But we know they have the same rational canonical form. So these are the same matrix. So the way that S and T act on these basis elements is the same. So there's a way to match up these basis elements and see that S and T really are the same linear transformation with respect to different bases. So we have seen that that means that how do you go between S and T? By some change of basis matrix, that this is equivalent to saying that S and T are similar linear transformations.